Welcome back. Here we are to speak more in detail about system integration of biofuels and fuel cells. In the last chapter, we have talked about the importance of the fuel preprocessing unit. That is something that is needed in a system to adjust the chemical composition of the biofuel in order to satisfy the requirements of the fuel cell that is implemented downstream. So the fuel preprocessing is may be designed in agreement with the strict requirements of each specific fuel cell technology. So the harmful compounds that have to be removed and addressed by the fuel preprocessing stage are many and differ according to the specific biofuel. Just to have an idea of the chemical compounds that we are addressing, here is a table. So we have sulfur, ammonia, halides, siloxane, and tars. Beside trace contaminants, the fuel preprocessing unit has to address also the bulk composition of the fuel. So also CO2, CO, methane, and small hydrocarbons may be an issue when it comes to some types of fuel cells. So looking at this table, we have a very general idea of the compatibility of each fuel cell technology with the specific chemical components that we may find in the gas. Looking at low temperature application like polymer electrolyte membrane, we know that hydrogen has to be fed with high purity. So carbon monoxide is a poison, so it has to be lower than 10 ppm. And also other small hydrocarbons are a poison. Methane can be fed to low temperature fuel cell, but it needs to be reformed, so it cannot be fed directly to the fuel cell. And then we have all other categories of contaminants that we may find in biofuel gas that are dangerous for this kind of fuel cell. The tolerance to carbon compounds and trace compounds increases going towards high temperature fuel cell. This because the higher temperature enables the internal reforming of both methane and small hydrocarbon, so we don't need to complete 100% reforming out of the fuel cell. And also some trace compounds are not dangerous for a high temperature fuel cell. Let's see, for example, tars. That is a particular category of hydrocarbon. It is a poison for polymer electrolyte membrane, but within low concentration, it is tolerated by high temperature fuel cells. So the removal of this component is less strict. Let's go more in detail about the most important biofuels that we have addressed in this course. Let's talk first about producer gas. Producer gas is a mixture of hydrogen, carbon monoxide, carbon dioxide, nitrogen, and some small amounts of halides, sulfur, and tars. So the low temperature fuel cell is more critical with this fuel, while the high temperature fuel cell can tolerate some of the contaminants and also the gas that are other than hydrogen. What happens if we want to feed producer gas to polymer electrolyte membrane fuel cell? We have to first clean the gas, so addressing sulfur, halides, and tars. After that, we have mandatorily a reforming stage and then a water gas shift reactor to remove carbon monoxide that is issued from the reforming stage. After this gas preprocessing line, we feed hydrogen to the fuel cell. The method that may be implemented to address the gas cleaning are many different ones at major technology level. They may be both cold methods like the water scrubbing, that is pretty state of the art, but also we have hot methods like the catalytic cracking. This last method is particularly nice when it comes to the decomposition of tars into smaller molecules that can be processed after. So producer gas into high temperature fuel cell can undergo an easier pre-treatment. This because still we have to remove sulfur halides in the gas cleaning stage. Tars is something milder, so we can still have some trace of tars in the gas that we feed to the fuel cell. So they don't have to be removed completely. Again, we can implement various methods in this stage, so cold methods like water scrubbing and hot methods. Hot methods in this particular application are more meaningful because of thermal integration issues. The solid oxide fuel cell or the molten carbonate fuel cell run over 600 Celsius degrees, and this enables the recovery of a lot of thermal energy that can be fruitfully employed in this stage of the system, increasing the overall efficiency of the system. So after the cleaning stage, we have the gas conversion and alteration, that in this case it's just a pre-reforming. This because the reforming reaction can be completed inside the fuel cell thanks to the occurrence of catalysts and also the high temperature. The product that we finally feed to the fuel cell is basically syngas. So again, we have a mixture of hydrogen, carbon monoxide and carbon dioxide that is not removed previously. So then we can analyze the case of biogas. That is maybe the biofuel that nowadays is most used. Looking at the chemical composition of biogas, we have a bulk structure made of CO2 and methane, and beside the major components we have some trace contaminants, mostly sulfur as hydrogen sulfide, but also siloxane. Sulfur again is a poison for all fuel cell categories, so we had to address strictly this problem. And also siloxane, there is evidence that they are dangerous for solid oxide fuel cell. This comes from literature studies, and we don't have specific information about the other fuel cell categories. Looking at a system layout scheme, so in the case of polymer electrolyte membrane, our system will be made of a gas cleaning stage, again to remove completely sulfur and siloxane, and then we have the reforming and water gas shift stage so that we can feed hydrogen to the polymer electrolyte membrane. In high temperature fuel cells, we have still the need to remove completely sulfur and siloxane, but this time we can implement also hot methods because, as we discussed also for producer gas, the high temperature fuel cell enable heat recovery, and high grade heat may be recirculated, may be recovered into the system and used to sustain the hot reactor where the gas cleaning is performed. After the cleaning, pre-reforming is done, and again we feed something similar to syngas to the fuel cell. So there would be some methane residual, CO2, hydrogen, and carbon monoxide. So the last biofuel that we are analyzing is bioethanol. So bioethanol is something easier to address when it comes to the chemical composition, because we do not have all the problems related to sulfur, halides, siloxane, and tars, but it's a more complex molecule. It is not methane, CH4, but it's a molecule where we have two atoms of carbons, five atoms of hydrogen, and one atom of oxygen. So the molecule has to be broken down and transformed in order to release hydrogen fuel for the fuel cell. Therefore, the main issue when it comes to use bioethanol is first the gas conditioning. We have to evaporate this liquid product, and then we have to provide a reaction that extract hydrogen from the bioethanol. So for polymer electrolyte membrane, we will have reforming and water gas shift to remove carbon monoxide, and so we have hydrogen to feed to the fuel cell. And when we have high temperature fuel cell, this would be a little bit easier, because after the evaporation of bioethanol, we can choose two ways. Either pre-reforming, so that we have things to feed to the fuel cell, or according to recent studies, there is also the possibility of feeding bioethanol vapor directly to the fuel cell, and then the decomposition of the molecule will happen directly into the fuel cell. So just to recap, what is the compatibility of biofuels with the most known fuel cell type? Polymer electrolyte membrane are market product. They are easy to manage, but they have some problems with bulk producer gas and biogas for what concern trace compounds and bulk composition. Bioethanol is easier to address in this kind of fuel cells. High temperature fuel cells are better for biofuels because we can continue the reforming of the gas inside the fuel cell and recover thermal energy that is useful to sustain the gas cleaning stage. Thank you for your kind attention.